The light hitting your eyes right now left the sun 8 minutes and 20 seconds ago. Not roughly, not approximately, exactly. And there is nothing, no technology, no physics, no amount of money or cleverness that can close that gap. The sun you are looking at is already the past. You're orbiting a memory, and you always have been. Now scale that up. The star on Orion's shoulder, Betelgeuse, is 600 years old in your sky. It may have already exploded. Andromeda's light left before our species existed, and 94% of every galaxy we can currently see is already permanently beyond our reach, sealed off forever by an expanding universe that is carrying them away faster than light can follow. Voyager 1 has been flying for nearly 50 years without stopping. It has not even reached 1% of the distance to the nearest star. This is the prison, not a metaphor. The actual, physical, measured dimensions of the cage the speed of light builds around everything that has ever lived on this planet. Hit like and subscribe if you have not. Get comfortable and maybe grab something warm, because tonight we walk every wall. We try every door. Warp drives, wormholes, generation ships, cryo-sleep, mind uploading. And we watch each one close, each in a different way. And then we ask the question, nobody warned us was coming. What if the cage is the only reason we exist to notice it? Let's get into it. Part 1. The slowest thing you are allowed to see. Right now, something is happening to your eyes that you have never once questioned, and when you finally do, it will quietly unsettle everything you thought you understood about the word now. Every single photon hitting your retina at this moment is old. Not metaphorically old, not philosophically old, literally, physically, measurably old. The light bouncing off this screen left a source some fraction of a nanosecond ago. The light coming through your window left the sun 8 minutes and 20 seconds ago. The faint glow you might see from a star tonight left that star decades, centuries, sometimes millions of years before you were born. You're not watching the universe. You're watching a recording of the universe, and the recording has no pause button, no rewind, and, here is the part that should bother you, no way to ever catch up to the original. We talk about the speed of a light the way we talk about a record breaker, 299,792,458 meters per second. We say it with admiration. We put it in the same sentence as Einstein and genius and the fundamental fabric of reality, and we mean it as a compliment. The fastest thing in the universe, the cosmic speed limit, the ultimate achiever. But that framing is exactly backwards. The speed of light is not fast. The speed of light is catastrophically, almost insultingly slow. And the only reason it doesn't feel that way is because everything you have ever personally needed to see has been within a few hundred meters of your face. The moment you zoom out even a little, the speed of light stops being impressive and starts being a prison wall, and the wall was already around you before you were born. Let's start with what light actually is doing when it travels. A photon leaves a source, a star, a screen, a candle, and it moves outward in every direction at the fixed speed, 299,792,458 meters per second. That number is not a suggestion. It is not a speed that can be exceeded with enough fuel, or enough cleverness, or enough time. It is a hard boundary written into the geometry of space-time itself. Nothing with mass can reach it. Nothing without mass can exceed it. It is the absolute ceiling of information transfer in this universe. And here is the thing about ceilings. They define what is above them as unreachable. When we say a star is 100 light-years away, we're not really talking about distance in the way you think about the distance to the grocery store. We're talking about time. We're saying that the information, the light, the signal, anything that could ever tell you what that star is doing right now, left that star 100 years ago and has been travelling toward you ever since, and it is only now arriving. The star you are seeing is not the star as it exists tonight. It is the star as it existed 100 years ago, when the photons that are currently entering your eyes were just leaving its surface. The star you see is a memory, and you have absolutely no way of knowing what the star is doing tonight, because tonight's photons won't arrive for another 100 years. This is not a quirk. This is not an engineering problem waiting to be solved. This is the structure of the universe. There is a concept in physics that sounds simple until you really sit with it, and then it sounds like the beginning of a very long, very quiet existential crisis. It is called the relativity of simultaneity, and it comes directly out of Einstein's special theory of relativity, published in 1905. The idea is this: there is no universal now, not in any physically meaningful sense. Two events that happen simultaneously according to one observer can happen at different times, according to another observer moving at a different velocity. Time is not a river flowing at the same rate for everyone. It is more like a collection of rivers, all flowing at slightly different rates depending on how fast you're moving and how strong the gravitational field around you is. What this means for us is radical and deeply strange. When you look at the night sky, you are not seeing a snapshot of the universe at a single moment. You are seeing a composite of moments spread across time, some photons from thousands of years ago, some from millions of years ago, some from billions, all arriving at your eye at the same instant but having left their sources at wildly different points in cosmic history. The night sky is not a picture of the universe. It is a collage of the universe's past, stitched together into something that looks coherent, but is actually a temporal patchwork where none of the subjects were photographed at the same time. Think about what that means for something as simple as communication. Imagine you are trying to talk to someone, but every message you send arrives at a delay that is physically impossible to reduce. Not technologically impossible, not economically impossible, physically impossible. The delay is baked into the geometry of the space between you. That is what the finite speed of light does to the universe. It turns every exchange of information into an exchange of history. You are never talking to the present. You are always talking to the past. There is a way physicists describe the reachable universe around any given point in space-time. They call it a causal bubble, or more formally, a light cone. The idea is that from any event, any point in space at any moment in time, there is a cone-shaped region spreading out into the future that represents everything that event can possibly influence, and a corresponding cone spreading back into the past, representing everything that could possibly have influenced it. Outside those cones, causality cannot reach. Events outside your light cone are not just difficult to communicate with. They are causally disconnected from you. They cannot affect you, and you cannot affect them, not in any way that the laws of physics permit. The speed of light, then, is not a speed limit the way a highway has a speed limit. It is the boundary of causality itself. It is the line between the universe you can participate in and the universe that is, for all physical purposes, not your universe at all. And here is the part that really gets under your skin once you let it. When you sit in a room and look around you, you are reconstructing reality from delayed signals. The coffee table is close enough that the delay is measured in nanoseconds, so it feels immediate. But the sun is 8 light minutes away, so the sun you see right now is 8 minutes old. The nearest star beyond our sun is over 4 light years away, so that star is over 4 years old by the time its light reaches you. Every single object you have ever seen in the night sky is a historical artifact. You have never, not once in your life, seen the present state of anything beyond this planet. You live inside a bubble of now that extends only as far as light can travel in a negligible amount of time. Step outside that bubble, which you do every time you look at the stars, and you are immediately in the past. Not metaphorically, literally, physically, measurably. Your present is built entirely from the past, and that is only the beginning of the problem, because we have been talking about seeing things. We have not yet talked about what happens when the things you need to see are not just distant, but operationally critical. What happens when the 8-minute delay is not a philosophical curiosity but a matter of survival? What happens when the object that is 8 minutes away is the sun itself, and you are trying to figure out if it is still there? Part 2. The 8-minute ghost. The sun problem. Here is a thought experiment that sounds ridiculous until you work through the physics, and then it becomes one of the most unsettling things in astronomy. The sun disappears. Not slowly, not gradually. Just gone. Instantly. In this hypothetical, the sun simply ceases to exist at exactly this moment, right now, as you read this. What happens on Earth? Nothing. For 8 minutes and 20 seconds, absolutely nothing happens. The light currently travelling from the Sun toward Earth, the light that was emitted 8 minutes and 20 seconds ago, continues on its journey. It arrives at Earth on schedule. The sky stays blue, the temperature stays the same. Your shadow is still cast on the ground in front of you. Every instrument, every eye, every solar panel on every satellite continues to behave as if the Sun is exactly where it has always been, doing exactly what it has always done. Because as far as the laws of physics are concerned, as far as anything in the observable universe can determine, the Sun is still there. And then, 8 minutes and 20 seconds after the Sun disappears, the last photon that ever left the Sun arrives at Earth's atmosphere, and the sky begins to go dark. But here is where it gets stranger, and this is the part that most people miss when they first hear this thought experiment. It is not just the light that is delayed, the gravity is delayed too. Einstein's general theory of relativity tells us that gravitational effects do not propagate instantaneously. Gravity travels at exactly the speed of light, 299,792,458 meters per second, the same speed, the same limit. A gravitational wave, the ripple in space-time caused by a change in a massive object's position or existence, travels at light speed. So if the Sun were to vanish, the gravitational field it has been exerting on Earth would not vanish at the same instant. It would continue to propagate outward from where the Sun used to be, following the same 8 minute and 20 second delay. What that means is extraordinary. For 8 minutes and 20 seconds after the Sun disappears, Earth continues to orbit a point in space where there is no Sun. The gravitational field still curves space-time in the pattern it always has, because the last gravitational information, the last signal telling space-time what to do, is still in transit. Earth follows that curve. It orbits nothing. It chases a memory. We are, right now, orbiting a memory. Not in the hypothetical, right now in reality, as things actually are. The Sun you are orbiting is not the Sun as it exists at this precise moment. It is the Sun as it was 8 minutes and 20 seconds ago. The gravitational information you're responding to, the curvature of space-time that is keeping you in your orbit, arrived 8 minutes and 20 seconds ago, and has been shaping your trajectory ever since. By the time any new information arrives, any update to the Sun's position, mass or condition, you have already been moving in response to the old information for over 8 minutes. This is the reality of our most intimate relationship with a star. The Sun, our parent star, the source of virtually all energy on this planet, the gravitational anchor of our entire solar system, is inaccessible to us in real time. We experience it with a delay. We feel it with a delay. We see it with a delay. The Sun we know is always slightly in the past, and there is no technology, no engineering, no clever workaround that can change that. The gap between the Sun that exists and the Sun we experience is not a gap in our knowledge. It is a gap built into space-time itself. Think about what that means when you watch a sunrise. You're watching an event that happened 8 minutes and 20 seconds before you saw it. You wake up, you look east, you see the Sun creeping above the horizon, and what you're actually witnessing is a replay, a slightly delayed broadcast of something that occurred almost 9 minutes earlier. The beauty is real. The physics behind it is deeply strange. And here is the thing. 8 minutes does not sound like much. In the context of everyday life, 8 minutes is how long it takes to brew coffee. It is nothing. It is negligible. The Sun is the closest star, the most intensely studied object in our solar system, bombarded with instruments and satellites and constant observation, and even we cannot close the 8 minute gap. Even with every tool humanity has ever built pointed directly at the Sun, we are always watching the past. Now take that 8 minute gap and start scaling it. The Sun is our nearest star. The next nearest star, Proxima Centauri, is not 8 light minutes away. It is 4.2 light years away. That is not 8 minutes. That is 4 years. The light delay from our nearest stellar neighbour is not a coffee break. It is a presidential election cycle. It is 2 Olympic Games. It is enough time for a child to go from newborn to preschool, and that is the nearest one. But we are getting ahead of ourselves. Before we get to the stars, there is something much closer that already demonstrates just how devastating this causal lag becomes the moment human beings try to do anything meaningful across it. You do not have to travel to another star system to experience communication deserts so profound they could cost people their lives. You just have to try to talk to someone on Mars. Part 3. The 40-minute conversation. Mars isolation. Mars is, by cosmic standards, practically in our backyard. It is the fourth planet from the Sun. At its closest approach to Earth, called opposition, it is roughly 54 million kilometers away. At its farthest, called conjunction when it is on the opposite side of the Sun, that distance balloons to over 400 million kilometers. In the language of a light travel time, that translates to somewhere between 3 minutes and 22 minutes one way. A signal travelling at the speed of light takes between 3 and 22 minutes to get from Earth to Mars, depending on where the two planets are in their respective orbits. 3 to 22 minutes, one way, double it for a round trip. At opposition, a conversation with a person on Mars would have a minimum round-trip delay of about 6 minutes. At conjunction, that round-trip delay is over 40 minutes. You say something, you wait 40 minutes for them to hear it, they respond. You wait another 40 minutes for the response to arrive. A question and answer exchange that on Earth takes 4 seconds would take, at its worst, 40 to 45 minutes. You would ask, "Are you okay?" and 3/4 of an hour later, you would hear the answer. Now let us stop being abstract about this and make it concrete, because the abstractness is what lets us mentally minimize what this actually means. Imagine there is an astronaut on Mars. This is not science fiction. NASA and other agencies have been planning crewed Mars missions for years, and the architecture for those missions has to confront this communication constraint as a fundamental design parameter. The astronaut is doing an EVA, an extravehicular activity, a spacewalk on the Martian surface, when something goes wrong, a suit malfunction, an unexpected pressure drop, a medical emergency. It does not matter what exactly. What matters is that they need help, and their lifeline, the only connection to every doctor, every engineer, every piece of institutional knowledge that could possibly save them, is 200 million kilometers away. They transmit a distress call. It leaves Mars at the speed of a light, 299,792,458 meters per second, as fast as anything in this universe can possibly travel, and it takes 11 minutes to reach Earth. Mission Control receives the call. They assess the situation. They formulate a response. The response leaves Earth at the speed of a light. It takes another 11 minutes to reach the astronaut on Mars. 22 minutes have passed. If the suit was failing when the call went out, the astronaut has been managing that failure alone, in real time, for 22 minutes, making decisions without guidance, without the reassurance of a human voice responding to their specific situation, without any way of knowing if their message was even received until the acknowledgement finally arrives. 22 minutes in a deteriorating spacesuit is not a manageable inconvenience. It is a survival situation unfolding in isolation. This is why mission planners describe Mars as inherently autonomous. Any crewed Mars mission will have to be designed with the assumption that the crew is on their own for any real-time emergency. The communication window is not a bandwidth problem. It is not a technology problem. It is a causality problem. Light has to carry the information, and light takes 11 minutes to make the trip one way, and there is nothing in physics that allows you to do it faster. You could build the most powerful transmitter ever constructed, and the signal would still take 11 minutes. You could use quantum entanglement, and no, before you ask, quantum entanglement cannot transmit information faster than light. We will come back to that. The gap is physical, not technological. And now think about what regular communication with a Mars colony would actually look like, not in an emergency but in everyday life. An astronaut on Mars sends a message to their family on Earth. "Happy birthday, thinking of you." That message takes 11 minutes to arrive. The family reads it, smiles, records a response. The response takes 11 minutes to get back to Mars, 22 minutes for a birthday greeting. Every conversation is asynchronous by necessity. You speak into a future you cannot see, and you receive answers from a past you cannot change. You develop a relationship with delay. You learn to live inside it. Submarine crews experience communication blackouts. Deep-sea research vessels have limited contact windows. Remote research stations in Antarctica sometimes go days between communications. But every one of those situations is a temporary technological constraint, a limitation of equipment, signal, or access that could theoretically be improved. The Mars communication lag is not improvable. It is not a limitation of our equipment. It is a limitation of causality, of the finite speed at which information can move through space-time, and it applies uniformly to every sender, every receiver, every signal, every frequency. The causal lag scales with distance. That is the rule. Every meter of additional distance between 2 points adds an additional 3 nanosecond delay to any communication between them. 3 nanoseconds per meter. It does not sound like much until the distance is measured in hundreds of millions of kilometers, and the delay is measured in minutes that could determine whether someone lives or dies. And Mars, we have to keep reminding ourselves, is our nearest planetary neighbour. Mars is the most realistic near-term destination for human beings beyond our moon. If the nearest place we can actually go already imposes 22-minute communication gaps, what does that tell us about the universe beyond the solar system? What happens when the distances are not hundreds of millions of kilometres, but trillions of kilometres? What happens when they are measured in light years? The answer starts with a spacecraft launched in 1977 that is, by any reasonable measure, still practically in our neighbourhood, and the lesson it teaches us about the scale of the prison is one that most people have never really sat with long enough to feel. Part 4. Voyager is still in the driveway. On September 5th, 1977, humanity launched a spacecraft called Voyager 1. It was designed to study the outer planets, Jupiter and Saturn, and then continue outward, becoming the first human-made object to leave the solar system entirely. It succeeded. Spectacularly. Voyager 1 has been travelling continuously for over 47 years. It is, by a considerable margin, the fastest human-made object in history. It is currently moving at approximately 17 kilometers per second. That is roughly 61,000 kilometers per hour. And it has been doing so without interruption for nearly half a century. Voyager 1 is currently approximately 165 astronomical units from Earth. An astronomical unit is the average distance from Earth to the Sun. About 149,600,000 kilometers, 165 of those. A signal from Voyager 1 travelling at the speed of light takes about 22.5 hours to reach us. Not days, not years, 22.5 hours. Do you know what 165 astronomical units converts to in light years? 0.0026 light years. Less than 3,000ths of a light year. The nearest star, Proxima Centauri, is 4.2 light years away. Our fastest spacecraft, after 47 continuous years of travel, has covered less than 1/16th of 1% of the distance to the nearest star. If you built a scale model of the solar system where the Earth-Sun distance was 1 meter, the nearest star would be about 275 meters away, almost 3 football fields. Voyager 1, after 47 years, would be at about 40 meters in that model, not at the nearest star, not halfway to the nearest star, not a tenth of the way, 40 meters out of 275, still in the driveway. That phrase, still in the driveway, does more work than any statistic can do on its own. Because when we talk about space exploration, we tend to picture Voyager 1 as this extraordinary achievement, this ambassador to the stars, this symbol of how far humanity has reached. And it is an achievement, it absolutely is. But it is an achievement measured against human timescales and human engineering, not against the actual scale of the universe. Against the actual scale of the universe, Voyager 1 has barely moved. Now let us put some more numbers around this to really let the scale land. The solar system does not end at Voyager 1's current position. The outer boundary of the solar system, the Oort cloud, the region where the sun's gravity still holds sway over loosely bound icy objects, extends outward to roughly 1 light-year from the sun, maybe more. Voyager 1, after 47 years, has covered about 0.0026 light-years. To reach even the inner edge of the Oort cloud, it would need to travel approximately another 10,000 astronomical units, and at its current speed, that would take on the order of several hundred years. To cross the entire Oort cloud and genuinely leave the solar system's gravitational sphere of influence, we're talking about tens of thousands of years of continuous travel. Tens of thousands of years. For comparison, the entire recorded history of human civilization, from the earliest writing in Mesopotamia to right now, is roughly 5,000 to 6,000 years. To reach the actual boundary of our solar system, Voyager 1 would need to travel for a duration longer than every war, every empire, every invention, every cultural shift, every written word in all of human history, multiple times over, and the nearest star is 4 times farther than that. At Voyager 1's speed, reaching Proxima Centauri from Earth would take approximately 73,000 years. Not 73 years, 73,000. Humanity did not exist in its current form 73,000 years ago. Modern humans, Homo sapiens with our current cognitive architecture, our capacity for language and complex thought, are estimated to have emerged roughly 300,000 years ago. 73,000 years ago, the Toba catastrophe, a massive volcanic eruption in what is now Indonesia, may have nearly wiped out the human species entirely. Agricultural civilization is about 12,000 years old. The invention of writing is about 5,000 years old. The Industrial Revolution is about 250 years old. The entire arc of recorded human progress, stacked end to end and multiplied by 6, would barely get our fastest spacecraft to the nearest star. And Proxima Centauri is the nearest one. It is the star next door. It is, by cosmic standards, essentially touching us. The Milky Way galaxy is about 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. Our galaxy is one of an estimated 2 trillion galaxies in the observable universe. The distances involved are not just large. They are so large that the word large has essentially lost meaning, and we need a new vocabulary to describe what we are talking about. The speed of light is not a prison wall in the sense that it is some external barrier that someone built. It is more like the speed of light defines the size of the cell, and the size of the cell is so enormous that you can live your entire life inside it without feeling confined, right up until the moment you try to leave. And then the wall appears, and it turns out the wall has been there the whole time. Voyager 1 is our most heroic attempt to leave. After 47 years, it has barely reached the first hallway, the door is nowhere in sight, and the question that ought to be keeping us up at night, the one we are building toward here, is whether there even is a door, or whether the hallway is the entire universe. But before we can answer that, we need to understand just how large the cell really is. And for that, we have to stop talking about our solar system entirely and start talking about what lies beyond it. Which brings us to the nearest door out of our immediate neighbourhood, 4.2 light-years away, and the sobering math of what it would actually take to get there. Part 5. The nearest door is 75,000 years away. Proxima Centauri sits 4.2465 light-years from our Sun. It is a small, red, dim star, a red dwarf, so faint that despite being the nearest star to Earth, you cannot see it with the naked eye. It has at least one planet in its habitable zone, Proxima b, which has inspired enormous amounts of speculation and research. It is the obvious first target for any serious interstellar mission, and getting there at our current best speed would take longer than our entire civilization has existed. Let us be very specific about what current speed means here. Chemical rockets, the kind that have gotten everything into space so far, from the first Sputnik to the most recent crewed missions, top out at effective speeds in the range of 30 to 40 kilometers per second for the fastest possible escape trajectories. At 40 kilometers per second, the trip to Proxima Centauri would take roughly 32,000 years. Better than Voyager 1's 73,000, but still 32,000 years. The Roman Empire rose and fell in under 1,500 years. 32,000 years before now, humans were painting cave walls and hunting mammoths. But surely, you might think, we can do better than chemical rockets. We are not wedded to those forever. What about ion drives, which are already used on some spacecraft? Ion drives are more efficient than chemical rockets, but produce tiny amounts of thrust. They're excellent for long missions, but would not dramatically change the trip time to another star. What about nuclear propulsion? Theoretical nuclear pulse propulsion designs, spacecraft that detonate a series of nuclear bombs behind them to generate thrust, could theoretically reach speeds of around 1% to 3% the speed of light. At 1% of light speed, the trip to Proxima Centauri takes about 420 years. Better, much better. But 420 years is still longer than the United States has existed as a country. What about fusion drives? Antimatter propulsion? These are the technologies that start appearing in serious academic papers about interstellar travel, and they can theoretically push spacecraft to a few percent of the speed of light. At 10% of light speed, an engineering achievement that would require solutions to problems we do not currently know how to solve. The trip takes 42 years, a human lifetime. A single person could, in principle, make the journey in their lifetime if they were launched young and arrived old. But 10% of light speed requires energy scales that are genuinely staggering, and the deceleration problem, how do you slow down when you arrive, is just as hard as the acceleration problem. And here is the thing that makes all of these numbers brutally clarifying. These are the travel times to the nearest star, not to the center of the galaxy, not to another galaxy, the nearest one, the smallest possible step beyond our solar system. And even with the most optimistic near-future propulsion technologies, we are talking about journey times measured in centuries at best, millennia at realistic speeds. This is where the prison metaphor stops being metaphor and starts being description. The cells of the prison are solar systems. The distances between cells are not corridors. They are voids so enormous that traversing them requires either the complete transformation of human biological timescales, the invention of propulsion physics that may not be achievable, or the willingness to commit to journeys longer than our entire recorded history. And beyond Proxima Centauri, the cells only get farther apart. The speed of light is not just limiting our travel, it is limiting our entire relationship with the universe. Every star you can name in the night sky is a prison cell, on the other side of a wall you cannot cross in a human lifetime without some kind of physics-defying breakthrough. And those breakthroughs, as we're going to find out, have a troubling habit of either requiring infinite energy or creating paradoxes that make the universe eat itself. But first, let us look up at the night sky, because the sky itself has something to tell us about the prison, something written in the light of stars that may not even exist anymore. Part 6. The sky is a graveyard. There is a star in the constellation Orion that has been worrying astronomers for years, and depending on when you're reading this, it may or may not still exist. Betelgeuse is a red supergiant star, one of the largest and brightest in our galaxy. It is so large that if you placed it at the center of our solar system, its outer atmosphere would extend somewhere past Jupiter's orbit. It is enormous in the way that makes you understand viscerally that our sun is a small star. And Betelgeuse is dying. It is in the final stages of its stellar life, a phase that ends in a supernova, an explosion so violent that for days or weeks, a single star outshines entire galaxies. Betelgeuse is approximately 700 light-years from Earth, maybe a bit more. Estimates vary between 600 and 800 light-years, let's say 700. What that means is that the light you see from Betelgeuse tonight left that star 700 years ago. It has been travelling through interstellar space for 7 centuries to reach your eye. The year 700 years ago was approximately 1325. Edward III was on the English throne. The Black Death had not yet arrived in Europe. There was no printing press. There were no firearms. There was no concept of the Americas as something Europeans could sail to. The light arriving from Betelgeuse tonight told you what Betelgeuse was doing in 1325. It told you nothing about what Betelgeuse is doing tonight. And here is the part that should genuinely give you pause. Betelgeuse is expected to go supernova. The astronomers who study it believe it will explode sometime within the next 100,000 years, which sounds like a long time, but is essentially any moment now on astronomical timescales. It could happen 1,000 years from now. It could happen 10,000 years from now. It could technically have already happened. If Betelgeuse exploded 200 years ago, and nothing in physics prevents that from being the case, the light from that explosion has not reached us yet. It is out there right now, 200 light-years away from Earth and closing, and we have absolutely no way of knowing it is coming until it arrives. We will wake up one morning, and where there was a dim point of orange light in Orion's shoulder, there will suddenly be a new object in the sky so bright you can see it in daylight. And that will be our first notification that 700 plus years ago, the largest object we can see with the naked eye ceased to exist. This is not a hypothetical about a distant corner of the galaxy. This is one of the most prominent stars in the night sky, and we are describing a situation where it could have already exploded, and we would simply not know yet, because the speed of light limits the rate at which that information can reach us. Now extend this principle to every star you have ever looked at. That faint star 2,000 light-years away. You're seeing what it looked like 2,000 years ago. That bright star 4,000 light-years out. Its light left before the Roman Republic became the Roman Empire. That cluster of stars 15,000 light-years toward the galactic centre. Their light is so old it predates modern human civilization by a comfortable margin. The night sky is not a window, it is a museum. Every object in it is a historical exhibit. You're not observing the current state of the universe, you're standing in a gallery of things as they were, arranged by distance and therefore by age, and nothing in the entire exhibition is showing you tonight. The sky is a graveyard. Not entirely. Most of those stars are still burning. But some of them are not. Some of the stars you can see right now have already exploded, already collapsed, already gone dark. You are looking at the light of things that no longer exist. You are seeing ghosts, and you will continue seeing them for hundreds or thousands of years after the actual stars they came from have died, because the light of their lives is still travelling toward you, and it takes as long as it takes. This is what causality looks like when you apply it at scale. The universe cannot send you faster updates. It can only send you the light it already emitted, at the speed the laws of physics allow, which means your view of everything beyond your immediate neighbourhood is always out of date by exactly the amount of time it takes light to cover the distance. For stars, that means years. For galaxies, it means millions of years. And for the farthest reaches of the observable universe, it means something so staggering it is hard to process without stopping and sitting quietly for a moment. Part 7. Andromeda Before Humans. On a dark, clear night, far from city lights, you can just barely see a faint smudge in the constellation Andromeda with your naked eye. It is not a star. It is not a nebula. It is a galaxy, the Andromeda Galaxy, also designated Messier 31, and it is the farthest object a human being can see without a telescope. It looks like a faint, elongated cloud, unremarkable at first glance, easy to overlook. But what you're looking at when you see that smudge is approximately 1 trillion stars. 1 trillion stars in a structure roughly 220,000 light-years across, located 2.5 million light-years from Earth. 2.5 million light-years. The light arriving at your eye from the Andromeda Galaxy tonight left that galaxy 2.5 million years ago. To put that in biological context, 2.5 million years ago the genus Homo had only recently appeared on Earth. Homo sapiens, modern humans, us, did not exist yet. The species that would eventually develop language, agriculture, civilization, science and telescopes would not evolve for another 2 million years. The photons currently landing on your retina from Andromeda have been travelling through intergalactic space since before our species existed. They have crossed 2.5 million light-years of void, threading through the intergalactic medium, arriving at a planet orbiting a star that was itself already several billion years old, to land on the eye of a creature that evolved 100 times more recently than the photon's departure date. You are, in a very literal sense, looking at the universe as it was before you were possible. This is where the central truth about the speed of light shifts from uncomfortable to genuinely overwhelming. The finite speed of light does not just delay our view of nearby things, it gives us access to an archive that spans billions of years of cosmic history. Telescopes are, at their core, time machines. The more powerful the telescope, the farther it can see, and the farther it sees, the deeper into the past it looks. The Hubble Space Telescope regularly images galaxies whose light travelled for 10 billion years before arriving at the detector. The James Webb Space Telescope has imaged galaxies whose light travelled for over 13 billion years, light that left its source a few 100 million years after the Big Bang itself, when the universe was a tiny fraction of its current age. This is the speed of light acting not as a prison wall but as something stranger, a time machine we can look through but not enter. We can see the past perfectly well. We just cannot interact with it, cannot reach it, cannot affect it in any way. The information arrives, we receive it. But we are always receiving it too late to do anything with it, except observe. And that observation, that passive, one-way receipt of ancient light, is the most we can ever achieve when it comes to most of the universe. Most of what exists is not just too far to visit. It is too far to ever receive any signal from in a meaningful time frame. And as we're about to discover, the universe has been busy making even that situation dramatically, catastrophically worse, through a process that is not science fiction, not speculation, not theoretical. It is the confirmed, measured, Nobel Prize-winning reality of the universe we live in. Most of the universe has already left the building. The door closed while we were still figuring out how to walk. Part 8. The 94% that is already gone. In 1929, An astronomer named Edwin Hubble published observations showing that distant galaxies are moving away from us, and not just moving away at velocities proportional to their distance. The farther a galaxy is, the faster it appears to be receding. This became the observational foundation of what we now call the expanding universe, the idea that space itself is stretching, carrying galaxies away from each other like raisins in an expanding dough. This was already strange enough, but in 1998, two independent research teams studying distant supernovae made a discovery so unexpected it upended cosmology entirely. They found that the expansion of the universe is not slowing down, it is speeding up. Something, a force or property of space itself that we call dark energy, which is a name for our ignorance as much as a description of anything, is causing the rate of cosmic expansion to accelerate. The universe is not just expanding, it is expanding faster and faster, with no end in sight. This acceleration has a direct and devastating consequence for the causal prison we have been describing. There is a sphere around us, centered on our location in the universe, called the cosmological event horizon. It represents the distance beyond which the expansion of space is carrying things away from us faster than light can cross the gap. This is a crucial distinction. The galaxies beyond this horizon are not moving through space faster than light. They are stationary in their local space, but the space itself between us and them is expanding fast enough that light, travelling at 299,792,458 meters per second through that space, is losing ground. It is like trying to walk toward the exit of an airport that is moving away from you faster than you can walk. Light that leaves a galaxy beyond our cosmological event horizon today will never, under any circumstances, reach us. Not in 1 billion years, not in 10 billion years. Never. The expansion of space will carry it farther away than it can travel. Those galaxies are not just far, they are causally disconnected from us. We are already out of contact, and the contact will never be restored. The observable universe, the sphere within which light from the early universe has had time to reach us, contains roughly 2 trillion galaxies. The cosmological event horizon, the boundary beyond which we can never receive new signals, is smaller. And here is the number that tends to stop conversations. Approximately 93 to 97% of the galaxies in the observable universe are already beyond our event horizon. The light we can currently see from them left long before the expansion carried them past the horizon, and it has been travelling toward us ever since, arriving as an echo of a reachable past. But no new light from those galaxies will ever reach us again. No new information, no new signal. Somewhere between 93 and 97% of everything we can see is already beyond our permanent reach. Permanently, causally, irrevocably. The cosmologist Lawrence Krauss and the astrophysicist Robert Scherer wrote a paper in 2007 that described what this means for astronomers in the far future. Billions of years from now, the expansion of the universe will have carried all but the closest galaxies beyond our event horizon. Future astronomers, if any exist, will look at the sky and see only the Milky Way and a few gravitationally bound neighbours called the local group. The rest of the universe will have expanded beyond the visible horizon. Those future scientists will have no way of knowing that the universe is, in fact, unimaginably larger than what they can see. The evidence will have physically expanded beyond their reach. The universe is, in a very real sense, progressively erasing its own history from the perspective of any given observer. Think about what this means for the central idea we have been building throughout this whole discussion. We began with the observation that the finite speed of light creates an unavoidable delay in our perception of everything beyond Earth. We scaled that up through the solar system, the 8-minute sun ghost, the 40-minute Mars lag, the 50-year voyage that barely reached the driveway. We scaled it up through the interstellar distances, the 73,000-year trip to the nearest star, the 700-year-old image of Betelgeuse. And now we have reached the cosmic scale, where the expansion of the universe itself combines with the finite speed of light to create not just a delay, but a permanent, unclosable disconnection from the majority of everything that exists. The prison is larger than we thought. The walls are farther away than we can see, and they are moving away from us faster than we can follow, which naturally raises the question, what if we could move faster? What if there were a way around the speed of light? What if the cage has a door we just have not found yet? We're going to open every door we know about. each one carefully, each one honestly, and we're going to watch them close. Part 9. Warp Drives. The Door That Burns You Alive. In 1994, a physicist named Miguel Alcubierre published a paper that should not have been publishable. Not because it was wrong, the math was correct, but because the math was correct, and what it described was a faster-than-light drive, a real one, grounded in general relativity, peer-reviewed, published in a legitimate physics journal. The Alcubierre drive works, conceptually at least, by not accelerating the ship at all. That is the trick. Einstein's relativity forbids accelerating any object with mass to or beyond the speed of light. But relativity says nothing about the speed at which space itself can move. The universe expanded faster than light immediately after the Big Bang. Galaxies beyond our event horizon are receding faster than light right now. Space is allowed to do things matter cannot. What Alcubierre proposed was a geometry of space-time that compresses space in front of the ship and expands it behind. The ship sits in a flat bubble of normal space-time while the space itself moves. From the ship's perspective, nothing unusual is happening. You're not accelerating, you're not moving faster than light locally, you're just sitting still in your bubble while space shuffles around you. From an outside perspective, the bubble, and the ship inside it, is travelling faster than light. You arrive at your destination before a photon that left at the same time by a direct route. The physics is internally consistent, the math works, and there are only a few problems, one of which is that the energy required to produce the space-time geometry Alcubierre described was originally calculated to require something approximating the energy equivalent of a Jupiter-sized mass converted entirely to energy. Not a Jupiter-sized object's worth of rocket fuel. A Jupiter-sized object's worth of E equals mc squared energy, the entire mass energy of a gas giant, to move a ship. In subsequent years, researchers including Harold White at NASA's EagleWorks lab worked on modifications to the geometry that could potentially reduce the energy requirement to something merely implausible rather than Jupiter scale. In the early 2020s, a series of papers revisited the mathematics and proposed new geometries that operated below the speed of light, while still offering interesting propulsion properties. The research continues. But here is what never gets discussed enough in the popular excitement about warp drives. Even if we solve the energy problem entirely, even if someone figured out how to produce the required exotic matter and geometry with a reasonable budget, there is a second problem waiting behind the first, and this second problem is where the speed of light reasserts itself as the enforcer of causality. When an Alcubierre-type bubble moves through space, it accumulates particles. Interstellar space is not empty. It contains hydrogen atoms, helium atoms, cosmic rays, photons, dust. Sparse, yes, but measurable. As the warp bubble moves, it acts like a plough, sweeping up these particles and accumulating them in the region at the front of the bubble. The faster the bubble moves and the farther it travels, the more particles accumulate. By the time it reaches its destination and decelerates, releasing the built-up particles, the forward direction of the ship experiences what some physicists have described as a burst of radiation and high-energy particles that would likely be lethal to anything inside the bubble, and potentially devastating to anything at the destination. You would arrive to find that your warp drive has just delivered a gamma-ray event to your destination. That is the engineering problem. The physics problem is worse. Any mechanism that allows faster-than-light travel also, in the framework of relativity, permits time travel, not as a side effect, as a logical consequence. If you can send information faster than light, you can, through a sequence of FTL jumps between observers in different reference frames, send information into your own past. This is not science fiction. It is the mathematics of special relativity applied consistently. An Alcubierre drive capable of genuine FTL travel would be a time machine, and time machines create causality violations, situations where effects precede causes, where you can prevent your own departure, where the logic of the universe becomes inconsistent. Physics has its own answer to this, called the chronology protection conjecture, proposed by Stephen Hawking. It suggests that the laws of physics conspire to prevent closed time-like curves from forming, that whenever a situation approaches creating a causality violation, some physical effect intervenes to prevent it. Whether that conjecture is correct is not yet known, but the pattern is consistent and worth noting. Every time we design an escape from the light-speed prison, causality waits at the exit with a problem that the escape route itself generated. The warp drive does not escape the prison. It runs into the prison's structural principle, the causal order of events, and the prison defends itself. The door opens, and behind it is not freedom. Behind it is a wall made of paradox. Part 10. Wormholes, the door that erases itself. Let us try a different door, a more exotic one. In 1935, Albert Einstein and his colleague Nathan Rosen were exploring the mathematics of general relativity when they discovered something strange embedded in the equations. The solution for a black hole, the region of infinite spacetime curvature that forms when mass collapses beyond a critical density, appeared to connect to another region of spacetime through what amounted to a mathematical tunnel. This was called an Einstein-Rosen bridge. Today we call it a wormhole. The original Einstein-Rosen bridge was not traversable. The tunnel collapsed faster than anything could cross it, even light. It was a mathematical curiosity, an artifact of the geometry, not a viable passage. But in 1988, physicists Michael Morris and Kip Thorne, the same Thorne who later won the Nobel Prize for gravitational wave detection, published a paper asking a different question. What would it take to make a wormhole traversable? What conditions would have to hold for an object, a person, a spacecraft to actually pass through? The answer was exotic matter, not exotic in the casual sense, exotic in a specific technical sense. Matter with negative energy density. Matter that pushes space apart rather than pulling it together. Matter that, in the equations of general relativity, produces a repulsive gravitational effect that would hold the wormhole's throat open long enough for something to pass through. Does such matter exist? In a specific quantum mechanical context, yes. Something called the Casimir effect demonstrates that the energy density between two closely spaced conducting plates can be measurably negative. But the amounts involved are microscopic, and scaling from Casimir effect quantities to enough exotic matter to hold open a traversable wormhole requires energy scales that make the Alcubierre drive look economical. Early estimates suggested you would need negative energy equivalent to the mass energy of something like the Earth to stabilize even a very small traversable wormhole. And then there is the causality problem again, because just like the warp drive, a traversable wormhole that connects two different points in space can be used to connect two different points in time. If you have a wormhole and you move one of its mouths at relativistic speeds, which time dilation makes possible, the two mouths end up at different points in time relative to each other. A signal or object entering one mouth exits the other mouth not just at a different location but at a different moment in time. Again, time machine. Again, causality violation. Again, the chronology protection conjecture waits at the exit. But there is a deeper problem specific to wormholes that does not even require the time travel issue. When physicists study the behavior of quantum fields inside a traversable wormhole, specifically, the vacuum fluctuations that quantum mechanics predicts exist everywhere in space, even in apparently empty regions, they find that those fluctuations build up at the wormhole's throat in a way that rapidly destabilizes the structure. The wormhole does not just close, it explodes in a burst of quantum mechanically generated energy before anything can cross it. The moment you create a traversable wormhole, quantum mechanics destroys it faster than causality can be violated. The universe, it seems, takes causality very seriously. The pattern here is not subtle. Both the warp drive and the wormhole are solutions to Einstein's equations of general relativity. Both are mathematically valid. Both describe geometries of spacetime that could, in principle, enable faster-than-light travel or communication. And both, when examined carefully, turn out to either require resources that are essentially impossible to obtain, create causality-violating time machines that physics then apparently prevents through various mechanisms, or destabilize through quantum effects before they can be used. The speed of light is not just a wall. It is a wall with active defenses. Every time you find a gap in the wall, the rules of physics close it before you can step through. And the closing is never arbitrary. It is always connected back to the preservation of causal order, the same causal order that the finite speed of light enforces in the first place. So forget the shortcuts. What about brute force? What if we do not try to beat the speed of light, but just accept the travel times and engineer our way around the biological problem of living long enough to arrive? What if the escape from the prison is not cleverness but endurance? Part 11. Endurance escapes. Time destroys the traveller. Suppose we accept the travel times. Suppose we acknowledge that there is no warp drive, no wormhole, no shortcut, and that the journey to the nearest star will take tens of thousands of years at achievable speeds, or decades at speeds that would require physics we cannot yet build. Suppose we decide to just go anyway. What does a realistic plan for that look like? The generation ship is the oldest idea in interstellar travel fiction, and the most literally interpreted in serious academic study. The concept is straightforward. You cannot send one person on a 70,000-year journey, but you can send a community. A ship large enough to house a self-sustaining population, equipped to maintain life across multiple generations, carrying not just the first crew, but the seeds of every subsequent crew that will live and die, and have children who live and die for the entirety of the voyage, until, eventually, some distant descendant of the original passengers steps off the ship at the destination. The mathematics of population genetics immediately establishes the minimum viable community size. A breeding population of around 40 to 80 individuals is often cited as a minimum for avoiding inbreeding collapse over centuries, but more careful analyses accounting for random genetic drift, founder effects, and the need for long-term genetic diversity push that number much higher. A comprehensive 2018 study by geneticist Cameron Smith suggested that a viable interstellar generation ship would need to launch with a founding population of somewhere around 10,000 people to maintain genetic health across a multi-generational voyage to the nearest stars. 10,000 people. A small town, launched into interstellar space for tens of thousands of years, and that is assuming the physics of keeping 10,000 people alive in a closed system for that duration, recycling every gram of water, every calorie of food, every litre of breathable air is solved, which is a set of engineering challenges that make a moon landing look simple. But the engineering is almost the easy part. The harder problem is cultural. A human language changes significantly in about 500 years. Modern English speakers cannot read Chaucer without study. In 1,000 years, the language spoken on the ship will be recognisably different from what was spoken at launch. In 5,000 years, it may be mutually unintelligible with the original. In 50,000 years, the timescale of a generation ship voyage at achievable speeds, the cultural, linguistic, and possibly cognitive continuity between launch crew and arrival crew becomes genuinely questionable. The knowledge base required to operate and maintain the ship is presumably encoded in documentation and systems, but over sufficient time, the relationship between a living culture and its preserved technical manuals changes. Instructions become tradition. Tradition becomes ritual. The manual for maintaining the drive becomes scripture, interpreted by those who can no longer distinguish its practical function from its ceremonial significance. There is nothing fanciful about this observation. It is what every human institution does with knowledge over sufficient time. It is what has happened to every set of instructions ever written down without ongoing living transmission. The ship launched by one civilization might arrive carrying something else entirely, not better or worse, necessarily, but different in ways that may or may not preserve the purpose of the original mission. So we turn to cryosleep. The alternative to living through the journey is not living through the journey, suspending biological processes for the duration of the trip and waking up at the destination as if no time has passed. This is perhaps the most common solution in science fiction, and it has a serious problem. We do not know how to do it with complex biological organisms without killing them, and the physics of what happens to biological tissue at the cellular level during extended freezing is not encouraging. The fundamental challenge is ice crystal formation. When cells freeze, water inside them forms crystals, and those crystals puncture cell membranes, causing irreversible damage. Vitrification, cooling so fast that water forms a glass rather than crystals, works for small samples and has been used successfully to preserve embryos and some organs for short periods. Scaling it to an entire human body is a problem of heat transfer physics that has not been solved, and even if you solve the freezing, you face radiation. Interstellar space is not empty, and a frozen traveller is not protected from cosmic radiation by the biological repair mechanisms that a living, active body uses continuously. Over decades or centuries of travel, accumulated radiation damage to DNA could be severe enough that revival is not possible. Then there is mind uploading, the idea that the self, the continuous thread of identity, memory, personality, is substrate independent, that it could be copied from biological neurons onto a digital substrate and run on a computer that can be kept on a ship indefinitely without the limitations of biological metabolism or radiation sensitivity. This is the door that looks the most promising at first glance and becomes the most philosophically vertiginous the longer you stare at it. The practical problems are formidable. We do not have anything close to the technology required to map a human brain at the synaptic level with sufficient fidelity to recreate its functional state. The Human Connectome project, begun in 2009, has been working for years and has mapped sections of mouse brain at nanometer resolution, which reveals a staggering complexity that makes full human brain mapping a project of incomprehensible scale. But set the practical problems aside for a moment, because the conceptual problem is more fundamental. If you upload your mind, create a digital copy of your neural architecture, and then the biological you dies, did you survive? The upload contains all your memories. It believes it is you. It will continue to believe it is you for as long as it runs. But there is a straightforward argument, made most clearly by the philosopher Derek Parfit, that the copy and the original are two different things. The original's experience ends. The copy begins a new continuous experience that happens to start with the original's memories. The copy experiences the arrival at Proxima Centauri. The original does not. Is that survival? Is that a solution to the problem of living long enough to complete the journey? The answer depends on your theory of personal identity, which is a problem philosophy has been working on for centuries without resolution. What is clear is that the speed of light, in forcing these travel times onto us, is not just challenging our engineering. It is challenging our understanding of what we even means across time. The causal isolation enforced by the finite speed of light scales at interstellar distances into a challenge to identity itself. The walls of the prison turn out to extend inward. They constrain not just where we can go, but who we can be when we get there. Part 12. The only things that make it aren't alive. There is a form of interstellar travel that sidesteps every single biological and identity problem we just discussed. It has been proposed seriously by major scientific organizations, backed with real funding and tested in preliminary form. It is also completely useless for the one thing most of us actually care about when we talk about interstellar travel, which is sending human beings to another star and having them arrive. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and Russian billionaire Yuri Milner with an initial $100 million research commitment, proposes sending a fleet of miniature spacecraft, not much larger than a postage stamp, equipped with a camera, a communication laser, and basic sensors, to Proxima Centauri using a ground-based laser array. The laser pushes a light sail attached to each tiny craft, accelerating them to approximately 20% of the speed of light. At that velocity, the trip to Proxima Centauri takes about 20 years. The craft arrive, spend perhaps a day in the system doing a flyby. There is no deceleration mechanism. They're going too fast to stop, and then transmit their data home, which takes another 4 years and change to arrive. 24 years from launch to data receipt. That is a human-scale timeline. It is an achievable engineering project in principle. It is the first genuinely plausible proposal for reaching another star system, and it sends a chip. No human, no consciousness, no experience of arrival. A camera and a laser briefly illuminating a distant star system with measurements, and then gone, still decelerating across interstellar space with no mechanism to ever slow down. The craft will never stop. They will not enter orbit around Proxima Centauri. They will flash through at 20% of light speed, take a few images and measurements in the time it takes to blink, and then sail on into the interstellar void forever. Machines succeed where biology fails. The speed of light's prison is survivable for machines, because machines do not have biological timescales. They do not age. They do not need to eat. They do not go insane during a centuries-long voyage. A von Neumann probe, a self-replicating robotic spacecraft, a concept first seriously outlined by mathematician John von Neumann in the 1950s, could theoretically colonize the entire galaxy in a few million years. It would mine asteroids for materials, build copies of itself, launch those copies toward the next system, and repeat. A single, self-replicating probe launched from Earth could, given sufficient time, fill the Milky Way with its descendants. Which brings us to something that deserves its own quiet moment of consideration. If self-replicating probes could colonize the galaxy in a few million years, and if the galaxy is several billion years old, and if there are billions of stars in the galaxy and a significant fraction of them host planets, and if life arose on at least one of those planets, ours, and developed technological civilization at least once, ours, then the statistical expectation is that the galaxy should already be full of von Neumann probes, launched by civilizations that preceded us by millions or billions of years, and we have not found any. This is the Fermi paradox, and it is directly relevant to the speed of light prison. There are essentially three families of explanation, and the speed of light is central to each. First, no one has ever launched self-replicating probes, either because technological civilizations are extraordinarily rare, or because they never develop the motivation or capability before something ends them. Second, self-replicating probes were launched, but something about the speed of light constraint causes the colonization process to stall out, perhaps because each generation of probes drifts in purpose over the timescales involved, or because the causal isolation between distant parts of a probe network makes it impossible to maintain coherent goals across galactic distances. Third, the probes are here, and we have not recognized them as probes. Each of these possibilities, examined closely, leads back to the same prison. Either the speed of light has prevented other civilizations from ever reaching us, or it has prevented them from maintaining coherent intent across the distances, or we are so isolated that we cannot even detect what may already be here. The causal structure of the universe enforces isolation not just for travel, but for information, coordination, and ultimately civilization-scale communication. The only successful interstellar travelers are machines, and when they succeed, presence is lost. There is no one on the other side of the journey. The escape from the prison removes the prisoner. Which brings us to the question we have been circling around since the very beginning. The question that every escape attempt forces us back toward. We have now watched every door close. Every shortcut either requires impossible energy, creates time travel paradoxes, destroys itself through quantum fluctuations, or demands that we sacrifice our biology, our identity, or our presence at the destination. The pattern is perfectly consistent, and perfectly consistent patterns in physics are not accidents. Part 13. The pattern. No one talks about. Let us stop and catalogue what just happened, because I think the list is worth reading slowly, not skimming, not half listening while you check your phone, actually reading, because the pattern embedded in this list is the whole point of everything we have been building toward, and it is easy to miss if you move through it too fast. We looked at warp drives. The Alcubierre geometry is mathematically valid. It does not break Einstein's equations, it works within them, which is what made it so exciting when it was first published in 1994, but the energy requirements are effectively impossible with any matter known to exist. And even if some future physics solve the energy problem entirely, the geometry itself creates a causality-violating time machine that the laws of physics appear to prevent through their own mechanisms. The universe does not simply say no to the warp drive because it is difficult. It says no because the warp drive, if it worked, would allow effects to precede causes, and the universe treats that as a more fundamental problem than any engineering challenge we could throw at it. We looked at wormholes. Einstein-Rosen bridges are real solutions to real equations. Traversable wormholes, of the kind Morrison-Thorne described in 1988, are theoretically possible structures, but they require negative energy at scales we cannot produce, and quantum field theory does something specifically hostile to them. The vacuum fluctuations that quantum mechanics says exist everywhere in space build up at the wormhole's throat and destabilize it faster than anything can cross. The wormhole does not just close slowly, it destroys itself through quantum effects before a single particle makes it through, and even if you somehow stabilized it, a traversable wormhole is also a time machine, which triggers the same causality protection response that killed the warp drive. Two different technologies, two different sets of equations, the same outcome, arrived at by a different route. We looked at generation ships. This is the one that does not fail through physics at all, it fails through time. The timescales involved in reaching even the nearest stars at achievable speeds are so enormous that cultural continuity, language, technical knowledge and institutional purpose erode across the duration of the voyage. A ship launched by one civilization may arrive carrying something genuinely different, not better or worse, but different in ways that may have no relationship to the original mission. The manual for maintaining the drive becomes scripture. The purpose of the journey becomes mythology. What lands at Proxima Centauri after 70,000 years is not the people who left. It is whoever those people became across a duration longer than all of recorded human history. The prison does not stop the ship. It transforms what is inside it beyond recognition. We looked at cryosleep, the biology of freezing complex multicellular organisms without killing them through ice crystal formation is not solved, and there are serious arguments that it may not be solvable at the scale of a full human body. But even setting that aside entirely, even imagining that someone develops perfect vitrification tomorrow, interstellar space is not empty, and a frozen body is not biologically repairing its DNA. Cosmic radiation accumulates over decades of travel, damaging genetic material continuously, and a frozen traveller cannot run the repair mechanisms that a living body uses constantly to manage that damage. So you have two independent, unconnected problems, the freezing problem and the radiation problem, and solving one does not touch the other. The prison finds two different locks on the same door. We looked at mind uploading. Here the failure is neither physics nor biology. It is philosophy, which turns out to be just as impassable. If you perfectly scan your neural architecture, copy every connection, every weight, every memory, every personality trait onto a digital substrate, and then the biological you ceases to exist, did you survive? The upload believes it is you. It has your memories. It will pass every test of continuity you could design. But there is a straightforward argument, made carefully by philosophers like Derek Parfit, that the copy and the original are two different things. The original's experience ends at the moment of copying. The copy begins a new experience that starts with the original's memories. Whether that counts as survival is not a question physics can answer. It is a question about the nature of identity and consciousness that has been debated for centuries without resolution. The prison, at interstellar distances, does not just challenge our engineering, it challenges our understanding of what we even are. We looked at light sail probes, and here, finally, something works. Breakthrough Starshot's architecture is physically achievable. Tiny spacecraft accelerated to 20% of the speed of light by ground-based lasers, reaching Proxima Centauri in roughly 20 years. The physics is sound. The engineering is difficult but not impossible in principle. The probes succeed, but they are not us. They are chips with cameras. They flash through the destination system at a fifth the speed of light, spend the equivalent of a long blink gathering data, transmit what they can, and then sail on forever into the interstellar void with no mechanism to stop. No human experience arrives. No consciousness makes the crossing. The escape from the prison is real and total, and the price of it is that nothing that matters, no presence, no awareness, no one to stand on new ground and look back at the star they came from, is on board. Every single escape attempt fails for a different reason. Warp drives fail because of causality. Wormholes fail because of causality and quantum mechanics. Generation ships fail because of time and culture. Cryosleep fails because of biology and radiation. Mind uploading fails because of identity and philosophy. Light sail probes succeed mechanically, but fail existentially, because nothing that experiences anything makes the trip. The specific failure modes are completely different in each case. The outcome is identical in every case. I want you to sit with that for a moment, because I think people move past it too quickly. We're not talking about 6 technologies that all happen to run into the same engineering wall. We're talking about 6 completely different categories of attempt. One in the geometry of space-time, one in quantum field theory, one in cultural anthropology, one in cellular biology, one in the philosophy of consciousness, one in mechanical engineering, and every single one of them closes. Each one closes differently. Each one closes completely. This is not a coincidence. Coincidences do not maintain perfect consistency across 6 completely different domains. When every escape route from a single constraint fails, each through different mechanisms, each arriving at the same outcome, the most honest explanation is not bad luck. It is not that we have not been clever enough yet. The most economical explanation is that the constraint is not incidental. It is not a wall that happens to be in the way. It is structural. It is written into the rules at a level that sits beneath any individual application of the rules, and every time one of our escape routes gets close enough to threaten it, the rules find a way to close the door using whatever materials are available. Causality here, quantum mechanics there, biology somewhere else, philosophy when nothing else is handy. The speed of light is not a limit imposed on top of a universe that would otherwise function perfectly well without it. It is closer to the opposite of that. It is the organizing principle around which the universe is structured. The reason every escape attempt fails is not that we keep bumping into the same wall from different directions. It is that the wall is not a wall at all. It is the skeleton. It is the load-bearing structure underneath everything else. Remove it, and the thing you are left with is not a freer universe or a faster universe. It is not a universe at all. Not in any sense we would recognize. It is something without causal order, without stable structure, without the conditions for complexity or chemistry or life or thought. But I do not want that to sound like a comfortable philosophical reframe, a nice way of saying the prison is actually fine, stop worrying about it. Because that is not what this is. This is a precise physical testable claim about the structure of space-time, and it has specific verifiable consequences that we can actually examine. To understand why the speed of light is not just a limit but a requirement, not just a constraint but a foundation, we need to look at what causality actually is, what it means for it to hold, and what a universe looks like when it does not. And that is where this whole thing finally turns. Part 14. The speed of light is the rule that makes reality work. Causality is the principle that causes precede effects. In our everyday experience, this seems obvious to the point of being uninteresting. You drop a glass, it falls, it breaks. The dropping causes the falling causes the breaking. The sequence has a direction. It cannot run backwards. Tuesday comes after Monday. The egg breaks before the omelette exists. The bullet leaves the gun before the wound appears. This is so fundamental to how we experience reality that it barely feels like a rule at all. It feels like common sense, like furniture, like something so basic it does not deserve to be named. But naming it turns out to matter enormously. Because causality is not just common sense. It is the organizing principle of everything we understand about physical reality, and it is far more fragile than it appears when you're only thinking about dropped glasses and broken eggs. Every physical law we know of is either consistent with causality or explicitly derived from it. Thermodynamics, electromagnetism, quantum mechanics, general relativity. Every framework we have ever constructed to describe how the universe works either assumes causal ordering or requires it as a foundation. Strip causality out of physics and you do not get a slightly different physics. You get something that does not function as a description of anything coherent at all. And here is the thing that most people never quite connect. The finite speed of light is not just related to causality. It is the mechanism that enforces it. It is the physical implementation of the rule. Without a finite maximum signal speed, causality has no teeth. It becomes a preference rather than a law. Here is why, and I want to go through this carefully because the logic is precise and the conclusion is genuinely strange. In Einstein's special theory of relativity, published in 1905, space-time has a geometry, not a metaphorical geometry, a literal, mathematical, measurable geometry in which space and time are combined into a single, four-dimensional structure. Events are points in that geometry, not events in the everyday sense of things happening, events in the physicist's sense, meaning a specific location in space at a specific moment in time. Every occurrence, every interaction, every quantum transition, every collision is an event, a point in space-time with 4 coordinates, 3 spatial and 1 temporal. The relationship between any 2 events in this geometry can be characterized in one of 3 ways, and which category applies determines everything about whether those events can be causally connected. If 2 events are separated by what is called a time-like interval, they can be causally connected. A signal traveling at less than the speed of light could, in principle, travel from one event to the other. One could cause the other. If 2 events are separated by a light-like interval, they sit exactly on the boundary. A signal traveling at precisely the speed of light could connect them, arriving at the second event at exactly the moment the first event's influence reaches that location. And if 2 events are separated by a space-like interval, no signal of any kind can connect them. They are causally disconnected. Whatever happens at one event cannot influence the other, not through any physical mechanism the laws of this universe permit. The speed of a light defines the boundary between these categories. It is the maximum signal speed, and therefore the maximum causal connection speed. The geometry of spacetime draws a cone, called the light cone, around every event, and everything inside the cone can be causally connected to that event, and everything outside the cone cannot. The surface of the cone is defined by c, the speed of light. Now here is where it gets strange. Suppose you could send a signal faster than light. Suppose you had a technology or a physics that allowed information to travel at twice c, or 10 times c, or instantaneously. What would happen? In the framework of special relativity, a signal that travels faster than light is, in some reference frames, a signal that travels backward in time, not as a metaphor, not approximately, exactly and literally. This is a direct mathematical consequence of the Lorentz transformations, the equations that describe how space and time coordinates change between observers moving at different velocities relative to each other. For any faster-than-light signal sent between two events with a space-like separation, there exists a valid reference frame, one moving at a sufficiently high but still sublight velocity, in which the signal arrives before it was sent. The effect precedes the cause. From that observer's perspective, the answer arrives before the question was asked. The wound appears before the gun fires. This is not a paradox in the dramatic science fiction sense of something surprising happening. It is a paradox in the logical sense, a direct contradiction, a statement that is simultaneously true and false, a breakdown of the consistency that makes physical description possible. If a faster-than-light signal can arrive before it was sent in some valid reference frame, and if reference frames are all equally valid descriptions of reality as relativity requires, then causality is not universal. It is reference frame dependent. And a causality that is reference frame dependent is not causality at all. It is noise. Think about what falls apart if you actually follow this through. If you can transmit a signal faster than light, you can, through a carefully arranged sequence of faster-than-light transmissions between observers in different reference frames, send information into your own past. You can receive the result of an experiment before you run it. You can receive a warning about an event before the event occurs, and use that warning to prevent the event, which means the warning was never sent, which means you never received it, which means you did not prevent the event, which means the warning was sent, and you are now inside a logical loop that has no consistent resolution. The universe's history is not a sequence anymore. It is a contradiction. The ordered structure of events, the chain of cause and effect that makes the universe's history a coherent narrative rather than a simultaneous smear of everything that ever happened, requires that no signal can travel faster than the maximum causal connection speed. It requires a finite c, not a large c, not a fast c, not a conveniently high c, a finite one, a hard limit. The specific value of c determines the rate at which causal influence can spread, but the finiteness of it is what makes causal order possible at all. So when we say the speed of light enforces causality, we do not mean it as a loose analogy, we mean it precisely. C is the number built into the metric of space-time that determines how space and time trade off in the four-dimensional geometry of the universe. It is not a property of light in particular. Light just happens to be a massless phenomenon, and massless phenomena travel at the maximum speed the space-time metric allows, which we call c, named after the Latin word for speed and associated with light because light was the first thing we measured travelling at that speed. Gravity waves travel at c, the strong nuclear force propagates changes at c. Information of any kind carried by any medium through any mechanism is bounded by c. It is not a speed limit on light. It is a speed limit on causality itself. A universe in which information could travel faster than c would not be a universe with a consistent causal structure. It would not be a universe where Tuesday reliably comes after Monday, where the egg can be confidently said to precede the omelette, where the history of the cosmos is a sequence of events rather than a superposition of all possible orderings of all possible events with no way to determine which caused which and which followed from what. The universe would not have a history. It would have something more like a fog. Every possible ordering of events simultaneously valid, no ordering privileged over any other, no way to build the persistent, stable, locally coherent structures that chemistry requires, that biology requires, that thought requires. There is a way of putting this that sounds almost too neat, but I think it is accurate. The speed of light is not the universe's speed limit. It is the universe's bookkeeping system. It is the mechanism by which the cosmos keeps track of what happened before what, assigns causes to effects in a consistent way, across all reference frames, and maintains the logical coherence of its own history. Remove C, and you do not free the universe from a constraint. You destroy the accounting system. And without the accounting system, the universe cannot accumulate anything. It cannot build atoms from particles, molecules from atoms, cells from molecules, organisms from cells, or the experience of reading this from the neurons of a brain that took 4 billion years of causally ordered chemistry to produce. The cage is the ledger. The prison is the reason the books balance. And the clearest way to see that, the most visceral, most immediate way to understand what a universe without C would actually look like, is to try to build one in your imagination, even briefly, and watch what happens to it. Part 15. A universe without the cage. Imagine a universe where the speed of light is not just faster than ours, but infinite. Not very fast, not effectively instantaneous, but truly without limit. In this universe, there is no delay between cause and effect across space. Information does not travel. It simply is, everywhere at once. Every change, every motion, every event, no matter how distant, becomes immediately known and immediately felt across the entire cosmos. At first glance, that might sound like an upgrade. No more waiting, no more isolation, no more unreachable stars or delayed signals. The entire universe would be connected in a single, seamless moment. But that intuition doesn't survive contact with physics, because the moment you remove the delay, the moment you remove the finite speed of light, you don't get a more connected universe. You get a universe that cannot hold itself together. Start with gravity, the quiet architect of structure. In our universe, gravitational effects propagate at the speed of light. When a massive object moves, the change in its gravitational field ripples outward at that finite speed like a wave spreading across a pond. This delay is subtle on human scales, but it is fundamental. It allows systems to settle, to stabilize, to evolve over time. Now remove that delay. In a universe with infinite signal speed, every change in the position of every mass, every star, every planet, every galaxy, is felt everywhere else instantly. The gravitational field is no longer something that propagates. It becomes a single, globally updated state, recalculated in real time across the entire universe. Picture what that means. A star shifts slightly in a galaxy 2 billion light-years away. In our universe, that change would take 2 billion years to reach us. In an infinite-speed universe, it is felt here immediately. At the same moment, countless other changes, stars exploding, galaxies colliding, black holes merging, are also updating the gravitational field everywhere, all at once. The result is not harmony, it is chaos. The gravitational landscape becomes a constantly shifting, infinitely interconnected web, where every local system is subject to the immediate influence of every distant event. Orbits cannot settle into stable patterns, because the forces acting on them are never isolated. A planet trying to circle its star would not just feel the steady pull of its sun, it would feel the instantaneous, ever-changing influence of the entire universe. Stable systems depend on a kind of quiet locality. They depend on the fact that nearby influences dominate, and distant influences arrive slowly, diluted by time and distance. Finite signal speed creates that locality. It allows a solar system to behave like a solar system, rather than like a node in a violently fluctuating cosmic network. Remove that constraint, and the idea of a stable orbit begins to dissolve. Planets would be constantly nudged, pulled, and perturbed by distant events that, in our universe, would never have had time to matter. The delicate balance that allows a planet to trace the same path around its star, year after year, would be replaced by a jittering, unstable trajectory. Over time, if time even remains a meaningful concept, those orbits would degrade, scatter, or collapse entirely. And gravity is just the beginning. Light itself becomes a problem of overwhelming magnitude. In our universe, the night sky is dark, a fact that puzzled astronomers for centuries and led to what is now called Olber's paradox. If the universe were infinite, eternal, and uniformly filled with stars, then every line of sight should eventually land on a star's surface. The sky should be as bright as the surface of the sun in every direction. But it isn't. The darkness of the night sky is protected by two key features: the finite age of the universe and the finite speed of a light. Light from distant stars simply hasn't had enough time to reach us, and the expansion of space stretches and dims what does arrive. Now imagine removing one of those protections. In a universe where light travels infinitely fast, distance no longer matters. Every photon emitted by every star in every direction across the entire universe arrives everywhere else instantly. There is no horizon, no delay, no redshift buffer to soften the intensity. Every line of sight terminates not in darkness, but in a stellar surface. The sky would not be black. It would not even be bright in the way we understand brightness. It would be a uniform, all-encompassing blaze, the combined radiation of every star in existence delivered simultaneously. The temperature of that radiation field would approach stellar surface temperatures. Planets, if they could form at all, would be bathed in a constant, unrelenting flood of energy. There would be no night, no shadow, no cooling period, no place for fragile chemistry to persist. Anything resembling a surface environment would be sterilized instantly. But the deeper problem is not heat. It is coherence. Our universe works because it allows regions to behave, for a time, as if they are independent. A cloud of gas can collapse under its own gravity to form a star. A protoplanetary disk can gradually assemble into planets. Chemical reactions can proceed step by step, building complexity from simplicity. These processes all rely on a kind of temporary isolation, a buffer between a system and the rest of the universe. Finite signal speed creates that buffer. It ensures that information about distant events arrives gradually, not all at once. It allows local conditions to dominate long enough for structure to emerge. It gives the universe time to compute itself in pieces, rather than being forced to resolve everything simultaneously. In an infinite speed universe, that isolation disappears. Every local fluctuation is instantly coupled to the entire cosmic environment. A slight imbalance in one region is not allowed to evolve independently. It is immediately influenced by conditions everywhere else. Instead of small contained systems developing their own dynamics, everything becomes part of a single global interaction. This has profound consequences for entropy and complexity. Complex structures, stars, planets, living organisms, are built in pockets of low entropy. They require gradients, differences, imbalances that can be exploited over time. But if every part of the universe is instantly aware of every other part, those gradients are smoothed out almost immediately. Energy redistributes globally, not locally. The universe trends toward uniformity far more efficiently. There is no time for complexity to take hold. You can think of it like trying to build a sand castle in a place where every grain of sand is instantly connected to every other grain. The moment you try to shape one part, the entire structure shifts in response. Nothing holds its form long enough to become anything more than noise. Causality, the simple idea that causes precede effects, is also at risk. In our universe, the speed of light acts as a boundary that preserves causal order. Events can only influence other events within their future light cone. This creates a consistent structure of before and after that all observers can agree on, even if they disagree about the timing. Remove that boundary, and the structure begins to unravel. If information can propagate infinitely fast, then in principle, influences can loop back on themselves in ways that blur or even invert cause and effect. The mathematical frameworks we use to describe space-time, those built on relativity, depend on a finite maximum speed. Without it, the geometry that defines causality collapses into something far less intuitive and potentially inconsistent. Even if a new form of order emerges, it would not resemble the kind of ordered step-by-step causality that allows processes to unfold, histories to form, and systems to evolve. It would be something closer to a single, all-encompassing state, constantly updating but never progressing in the way we understand progress. And that brings us to the deepest layer of the problem. Complexity is not just about having many parts. It is about having parts that can interact, adapt, and build on previous states over time. It is about memory, persistence, and the accumulation of structure. All of that depends on delays, on the fact that not everything happens at once. Finite signal speed is what gives the universe its rhythm. It spaces out interactions. It creates sequences. It allows one event to lead into another, rather than being drowned out by the simultaneous influence of everything else. It is, in a very real sense, the pacing mechanism of reality. In an infinite speed universe, that pacing disappears. Everything becomes immediate, everything becomes global, and in that immediacy, the universe loses the ability to tell a story. There are no chapters, no transitions, no gradual developments, only a constantly shifting, fully connected state that never settles into anything stable enough to remember. No stars as we know them, no planets, no chemistry unfolding over billions of years, no biology inching its way from simple molecules to conscious observers, no observers at all. Which leads to the inversion at the heart of this idea. The speed of light, the thing that seems to limit us, to isolate us, to trap us inside tiny pockets of space and time, is also the thing that makes those pockets possible. It is the reason gravity can build stable systems instead of chaotic ones. It is the reason the night sky is dark enough for planets to cool and life to persist. It is the reason local regions of the universe can develop their own histories, their own structures, their own complexity. It is the reason anything can exist long enough to become something. The cage is not preventing us from having a better universe. The cage is what allows there to be a universe that can have anything at all. And inside that constraint, inside that finite speed, that enforced delay, that quiet isolation, something remarkable happens. Matter organizes. Stars ignite, planets form, chemistry becomes biology, biology becomes awareness, and awareness turns back on the universe and asks a question. Why does it feel like we are trapped? The answer may be simpler and stranger than it seems. We are not trapped in spite of the speed of light. We are here because of it. Part 16. The final reframe. The cage is a shelter. Come back with me for a moment to the things we have been circling, not as abstract ideas, but as lived realities that quietly define every second of your existence. The sun you see right now is not the sun as it is. It is the sun as it was 8 minutes and 20 seconds ago. The photons touching your eyes left its surface before you finished your last thought, before you shifted your posture, before you even decided to look up. You're not looking at a star. You're looking at a memory of a star, carried across space at the maximum speed the universe allows anything to move. That delay is so small on human scales that it feels negligible, but it is not nothing. It is the beginning of the pattern. Push outward. Betelgeuse hangs in the night sky, steady and familiar, its reddish glow one of the most recognizable sights in the constellation of Orion. But the light that defines its shape in your sky tonight began its journey roughly 600 to 700 years ago. When those photons left Betelgeuse, human civilization was in a completely different state. Entire empires have risen and fallen in the time it took that light to reach you. There is no way, from here, now, to know what Betelgeuse is doing. It may still be there, burning in its final unstable phases, or it may have already exploded in a supernova, its outer layers tearing outward into space, a transformation that, from our perspective, has not happened yet. The event, if it has occurred, is already written into the structure of space-time, but we are waiting for it, locked behind a delay we cannot bypass. Push further still. Andromeda Galaxy drifts toward us across the dark, a massive spiral galaxy containing hundreds of billions of stars. Its light takes about 2.5 million years to arrive. What you see when you look at Andromeda is not just distant in space, it is ancient in time. The photons entering your eyes tonight began their journey before Homo sapiens existed in their current form, before language, before culture, before anything you would recognize as human history. You're not observing a galaxy as it is. You're observing a fossil record of light, an image frozen at a moment so far removed from your own that the word present loses any meaningful connection. And then there is the horizon. Not a physical wall, not something you could travel to and touch, but a boundary nonetheless. The cosmological event horizon. Because the universe is expanding, and because that expansion is accelerating, there are regions of space whose light will never reach us, no matter how long we wait. Galaxies beyond a certain distance are receding from us faster than light can bridge the gap. Not because they are moving through space at superluminal speeds in the usual sense, but because space itself is stretching between us and them. The result's the same. Their light, emitted today, will never arrive. Their future is permanently disconnected from our own. Estimates suggest that roughly 94% of the galaxies in the observable universe are already beyond this horizon, already gone, in the only way that matters physically. Their past light may still be arriving, ancient photons that left when the universe was younger and smaller, but their present and future states are sealed off. There is no signal you could send that would ever reach them. There is no journey you could begin that would ever arrive. When you first encounter these facts, they feel like losses. They feel like constraints imposed on an otherwise open universe. The 8-minute delay of the sun feels like a small but unsettling disconnection. The centuries-long delay of Betelgeuse feels like uncertainty, like watching a live broadcast that may already be out of date. Andromeda's millions of years feel like an unbridgeable gap between observer and observed. The cosmological horizon feels like a door closing, not just far away, but closing everywhere, in all directions, all at once. It is natural to interpret these as the dimensions of a prison. The walls are measurable, the delays are quantifiable, the isolation is real. We are confined, in a very literal sense, to a region of space-time defined by the finite speed at which information can travel. Every observation you have ever made, every image you have ever seen, every signal you have ever received has obeyed that limit. There are no exceptions. There is no workaround. The universe does not allow information to move faster than this speed, and because of that, there are parts of reality that are, in principle, forever inaccessible. But what we have been building toward is the recognition that this confinement is not simply a restriction. It is a condition. The finite speed of light is what makes causality possible, and causality, the ordered relationship between cause and effect, is what makes the universe intelligible at all. If information could propagate instantly or arbitrarily fast, the sequence of events would lose its structure. Causes could not be cleanly separated from their effects. Interactions would not unfold over time in a way that allows stable patterns to emerge. The universe would not have a history in the way we understand it. It would have something closer to a simultaneous blur of interactions, a state in which everything influences everything else at once, with no meaningful delay, no separation, no locality. That kind of universe is not just different. It is hostile to structure. The formation of atoms depends on stable interactions between particles over time. Chemistry depends on predictable relationships between those atoms. Biology depends on the persistence of chemical systems that can store and replicate information. All of this requires a kind of causal insulation, the ability for a local region of space to evolve according to its own internal dynamics, without being instantly overridden by every other event in the universe. The speed of light enforces that insulation. It ensures that influences take time to propagate. It creates a finite causal radius around every event, a region within which effects can spread and beyond which they have not yet reached. This is what allows stars to form from collapsing clouds of gas, rather than being constantly disrupted by distant gravitational fluctuations. It is what allows planets to settle into stable orbits, rather than being endlessly perturbed by instantaneous changes across the cosmos. It is what allows energy gradients to persist, entropy to increase in an orderly way, and complexity to arise in pockets where conditions remain stable long enough. Without that finite speed, there is no separation. Without separation, there is no stability. Without stability, there is no complexity. And without complexity, there is no one to notice any of this. The isolation we experience, the fact that we cannot see the sun in real time, that we cannot know the current state of Betelgeuse, that we cannot interact with most of the universe, is the same isolation that protects the delicate processes that built us. It is the reason atoms can bind into molecules without being constantly disrupted by distant events. It is the reason those molecules can assemble into cells, those cells into organisms, and those organisms into systems capable of perception, memory, and thought. We are not just observers of a universe constrained by the speed of light. We are products of those constraints. Every atom in your body was forged in the core of a star, in a region of space-time where causal relationships unfolded in a stable, predictable way. Those atoms were ejected into space, incorporated into new structures, eventually becoming part of a planet that orbited its star in a narrow band of stability. Over billions of years, under conditions that required precise balances of energy, temperature, and chemistry, life emerged. That life evolved, increasing in complexity, developing mechanisms to sense and respond to its environment, eventually producing a brain capable of modeling the world, of asking questions, of noticing patterns. all of that depends on the consistency of the speed of light. It is not just that light travels at a fixed speed. It is that this speed is the same everywhere, for all observers, regardless of their motion. This invariance is one of the foundational principles of relativity, and it underpins the entire structure of space-time as we understand it. It ensures that the ordering of events is preserved in a way that allows for coherent narratives of cause and effect. It prevents paradoxes that would otherwise arise if signals could be sent into the past. It maintains the integrity of physical law across the universe. In that sense, the speed of light is not merely a limit, it is a rule that everything follows, without exception. A rule that defines the maximum rate at which influence can propagate. A rule that shapes the geometry of space-time itself, determining how distances and durations are measured, how events are related, how the universe evolves. When you look at it from this perspective, the language of imprisonment starts to shift. Yes, there are walls. Yes, there are regions we cannot reach, signals we cannot send, information we cannot access. Yes, the vast majority of the universe is, in a practical sense, forever beyond us. Those are real constraints, and they are not going away. But those same walls are load-bearing. They are not arbitrary barriers imposed on an otherwise open system. They are the structural elements that hold the system together. Remove them, and the entire architecture collapses. The universe becomes something else entirely, something in which the conditions necessary for structure, for complexity, for life, are no longer met. You look at the night sky and you see ancient light, delayed signals, ghosts of stars and galaxies that may no longer exist in the form you perceive them. It is easy to interpret that as a kind of cosmic loneliness, a sense that we are cut off from the rest of reality, confined to a small, local bubble. But that bubble is precisely what made you possible. It is a region where causal relationships have been stable enough, for long enough, to allow matter to organize into increasingly complex forms. It is a pocket of space-time where the laws of physics have unfolded in a consistent, predictable way, enabling the long chain of events that leads from the Big Bang to the present moment. It is, in a very real sense, a shelter. Not a shelter in the comforting, protective sense we usually imagine, but a shelter in the structural sense, a set of conditions that make a certain kind of existence viable. We are not trapped inside a limit. We are sustained by a constant. The speed of light, in its absolute, unbreakable consistency, is the thread that connects every event in the history of the universe. It is the rate at which information flows, the pace at which causes become effects, the rhythm that governs the unfolding of reality. It is what allows the universe to have a past that leads into a present that can influence a future. Without it, there is no sequence. Without sequence, there is no story. Without story, there is no meaning. And yet, even within these constraints, the scale of what we can observe is staggering. 2 trillion galaxies, each containing billions of stars, their light travelling across vast distances and times to reach us. We are embedded in a system that is both limited and immense, confined and expansive, bounded and yet filled with more structure than we can fully comprehend. The night sky is a window, a one-way, time-delayed, frame-limited window, but a window nonetheless. Through it, we can see the deep past of the universe, reconstruct its history, infer its structure, test our theories against observations that span billions of years. We can map the expansion of space, measure the cosmic microwave background, trace the distribution of galaxies, and piece together a coherent picture of how everything came to be. That we can do this at all is not despite the speed of light, it is because of it. The question, then, is not whether we can escape this structure. All evidence suggests that we cannot. The constraints are fundamental, woven into the fabric of space-time itself. Every proposed workaround of faster-than-light travel, wormholes, exotic space-time geometries, runs into deep theoretical and practical problems, many of which seem to point back to the same underlying principle, the preservation of causality. The question is whether we understand what these constraints have given us. Standing here, on a small planet orbiting an ordinary star, in a galaxy that is one among billions, inside a universe that is mostly beyond our reach, we have the ability to look outward and piece together a story that spans from the earliest moments after the Big Bang to the present. We can measure the speed of light, calculate distances, identify horizons, and recognize the limits of our access to reality. we can also recognize that those limits are not arbitrary. They are the conditions that made the entire chain of events leading to our existence possible. The speed of light is a prison, in the sense that it confines us to a finite region of space-time and prevents us from accessing the rest. The walls are real, the isolation is real, the distances are real, but the prison is also the architecture. The same constraint that keeps us in is the one that holds everything up. It is the reason the universe has structure, the reason it can support complexity, the reason it can produce observers at all. You're not looking out from inside a cage at a universe you cannot reach. You are looking out from within a carefully structured system that made you capable of looking, and the light that reaches your eyes, delayed, finite, constrained, is not just evidence of what is out there. It is evidence of the rule that made seeing possible in the first place. We are not trapped inside the universe. We are sheltered inside the conditions that allow the universe to be known. And perhaps the most remarkable thing is that, within those conditions, we have just begun to understand what we are looking at.